Hello everyone, I'm Amir Aghdam, and in this lecture I'm going to give an overview of the paper Encoder-Decoder with Atrous separable convolutions for semantic image segmentation. As the name suggests, this paper was mainly proposed for the task of image segmentation and has gained some competitive results in the famous benchmark like COCO or Cityscape or ImageNet, and is one of the most state-of-the-art models that we're going to explore in a second. So let's get started. And before getting into the details of the architecture of this model, I'm going to have to give an overview of how and why this model has been proposed in the first place. So there's two main motivation and two main architectures that has been incorporated in most of the convolutional neural networks used for semantic image segmentation. And one of them is the special pyramid pooling. And what it's trying to do in the most of the architectures, like PSPNet or the previous versions of this paper, I mean the DeepLab version 2, version 3, and all of the papers have used this kind of special pyramid pooling module. What this module tries to do in most of the architectures is that it tries to capture an input image, the features of an input image from different scales, and it would help to network to learn the objects that are in different scales, and it gives the network multiple fields of view from the input image. The second most important encoder, the architecture, is the encoder-decoder, and I guess you guys, if you ever read the semantic image segmentation papers, you have definitely came across with these architectures. And what this is trying to do, the encoder-decoder, is that it is composed of two main modules, which is encoder and the decoder. The encoder tries to reduce the feature map size of the input image by trying to do convolutions and pooling operations, and the decoder module tries to upsample and recover these special features according to the decoder module. So we're going to explore all of these in details, but what I'm trying to say is that the main novelty that this paper is proposing is that if we incorporate these two famous architectures, we can gain some substantial improvements in the famous benchmarks. So we're going to see how this works and how this architecture is incorporating these two methods. As you might have known, these two methods have their own merits and advantages, and by incorporating them, we are actually exploiting both merits of these methods. As the paper suggests in the introduction, the special pyramid pooling module tries to reach contextual information by pooling features at different resolutions, and the latter one, which is the encoder-decoder, is able to obtain sharp object boundaries. And by combining these two methods, we can gain very, very competitive results in the famous benchmarks. So, as I mentioned earlier, we have this incorporation of these two architectures indicated in here. As you can see, we have the special pyramid pooling, which is just like the same architecture of the version 3 of the DeepLab. And you have a downsampling road in here, which is downsampling in each step with a factor of 2. And at the ending layer, we have the special pyramid pooling module, which tries to get an overview at different scales of the feature maps that have been resulted from the last convolution. And by doing that, we're actually capturing the multi-scale information from the from our feature map that has been resulted from this last layer. So what we're doing after that is that we're upsampling all of the aggregated feature maps in one move to output the mask that we're intending to get from the network. And by doing that, we're losing an extra amount of spatial information, which is not favorable for our task in image segmentation. And the encoder-decoder module is practically doing the same in the road of the encoder module, which reduces the resolution of the image and tries to compress the resolution into the bottleneck, which is, in case of encoder-decoder, the last layer of the encoder is called bottleneck. And after the bottleneck, we're trying to upsample it in each step to gain the original size of the image, which is the mask that we're expecting to gain from the input from the network. So what we're doing here is that we're actually trying to combine these two architectures to gain a final unified architecture, which is encoder-decoder with Atrous convolution and also with a spatial pyramid pooling module to be able to capture objects from different scales. It actually gives the network the ability to see the feature maps from different fields of views. So after we aggregate all of that, we are not upsampling it in just one move. And what we're doing here is that we upsample it by the factor 4, and in the next step, we upsample it in another 4-factored upsampling. And this is done by the method of bilinear upsampling, which is a method that you can go over the details of it. You can search the name of it. It basically tries to upsample it according to the neighboring pixels of each pixel, the 4 neighbor pixel of the feature map, and it uses this information to upsample it. And this is called the bilinear upsampling. And the main difference between the first version that we're seeing here is that we're just incorporating an extra decoder module here to better capture the spatial information and offset for the spatial loss that we're actually having in these types of tasks. So another method that has been proposed instead of using the encoder-decoder is that we can keep the resolution constant, or at least by factor 4 or 8 is smaller than the input resolution, and this will give us the enough spatial information to give an accurate result for our input image and get a better mask. But this may not be practical in the concrete applications because that would be computationally prohibitive for us to implement. So on the other hand, we have the encoder-decoder models that are faster in computation, in terms of computation, and we can use this with the along with the Atrous convolution and to gain better results. And this is what the paper is suggesting to do. And if I want to summarize all of the novel ideas that has been proposed in this architecture, is that we are utilizing an encoder-decoder structure according to in comparing to the DeepLab version 3, which is just an encoder or just a unified model without any decoder, and we're just adding a decoder module. And in our structure, as can be seen in here, we are using the Atrous convolutions, or AKA dilated convolutions, to trade off between the precision and runtime. So you can choose the output resolution considering your available resources and computation resources to gain better accuracies. And the using of Atrous convolutions gives us the ability to control the resolution. So this is just one of the novel ideas that has been proposed in the DeepLab paper series. So another novel idea that has been incorporated in the design of this model is using the backbone of exception. You can definitely use various architectures for the backbone of this model, like ResNet or MobileNet. But in this case, in this paper, it has been proposed that exception model would work better, and there has been some modifications made into the original design of it to better fit our task, and we'll see how are these modified in just a few seconds. So the related works in this area generally use 3 methods in their architectures. The first one is spatial pyramid pooling, modeled like PSPNet or DeepLab. I mean, the previous versions and this version are all using spatial pyramid pooling. And the encoder-decoder architecture that we just went through all of the details of it. And the depth-wise separable convolutions are 3 main points that have been exploited to make a unified architecture that can have a competitive result on the task of segmentation. So as it is indicated in this picture, you can see that the whole architecture that is brought about in just one image. You can see that we have a deep convolutional neural network here, which is used as a backbone model for feature extraction. It could be anything. It just depends on the choice that we have. But the experiments conducted on this matter shows that the modified exception for this feature extractor and backbone model works better than the others. And after that, we have pyramid pooling, as you can see in here, and we apply different convolutions with different sampling rates, like rate of 6, rate of 12, rate of 18, as you can see in here. And after doing this, we will aggregate all of the feature maps that has resulted from these, and we aggregate all of them and concatenate them. And finally, we would apply a 1-by-1 convolution on all of them to reduce the channels and the dimensionality of the data. for computational complexity purposes. And in the next part, we upsample it by a factor of 4. And what we're trying to do here is that after doing that, we want to use some of the low-level features from the deep convolutional neural network, and we connect the output of one of the low-level features to the decoder model, and we will do the same similarly to this part, a one-by-one convolution to reduce the number of channels, and finally, we will concatenate them. And after doing a 3x3 convolution to smoothen the result, we would upsample it by a factor of 4 to generate the mask that we're intending from the network. So this is the whole architecture that is proposed by the paper. As you can see, we have just 2 modules, which is the first one encoder, the second one is a decoder, and we have incorporated the model of the DeepLab version 3, which is this part, and we've just added another module, which is a decoder, to better recover the spatial information from the features. And that is how this model has been implemented. So in the upcoming sections, we will explore some of the methods that has been used in the architecture. One of them is the encoder-decoder with Atrous convolution. We previously mentioned the use of Atrous convolution in this architecture, but we've never get into the details of how this works. We can generally say that a regular convolution is actually is just a subset of the Atrous convolution. What I mean by that is that the Atrous convolution has an extra parameter, which is the sampling rate, and it defines the field of view of our network. As you increase the field of view or the sampling rate, our kernels gets dilated, and you can increase the field of view of the network to better capture multi-scale information from the input image. So that's how we use this, and this is the Atrous convolution, and you can see here the formula that has been indicated for this operation. Actually, I think this is for the 1D or one-dimensional Atrous convolution, and the R factor or R parameter that you see in this part is actually the sampling rate that we're using to output feature map. So you can say that the regular convolution is just a generalization. The Atrous convolution is just a generalization of the regular convolution, which the rate in the rate parameter in the standard convolution is just 1, and you can say that the regular convolution is just a Atrous convolution with the sampling rate 1. The second method that has been used in this architecture is the depth-wise separable convolution. What I refer to as the depth-wise separable convolution is that we will substantially reduce the amount of computation needed to do the convolutional operation by doing depth-wise separable convolution. This operation could be generally categorized or divided into 2 steps. The first one is a depth-wise convolution, and the second is the point-wise convolution. So you do this to reduce the computation complexity. And how you do this is that first you apply the depth-wise separable convolution to just each channel for each input channel, and the output of that depth-wise convolution is just has the same number of channels as the input image or input feature map. And after acquiring that, you just do the one-by-one convolution to generate the desired amount of channels that you want to have as your feature map. So you just transform once, and then you just increase the number of channels by applying one-by-one convolution the number of times you want to do that. So that's how the depth-wise separable convolution decrease the computation complexity. And as you can see in this part, this process has been divided into 3 steps and illustrated as shown in here. You can say that we first apply the kernel to the same number of channels that we have, and we generate the same number of channels as the input. So you can say that we have 3 channels in here, and the output is the 3, as you can see. Then we apply the point-wise convolution, which is a one-by-one convolution, to generate the number of channels that we want to do. And we're going to exploring another variant of this method, which is the Atrous depth-wise convolution. And we just everything is the same, and we just change the rate of the convolution. And by rate, I mean we dilate this kernel, and that would give us something like this. So the next thing that we might want to consider in this architecture is that in the encoder-decoder architecture, we have used DeepLab version 3 as the encoder, and the thing that is saying in here is that the we call the output stride, or we refer to output stride as a ratio of input image to the spatial resolution to the final output resolution. So for doing that, the paper gives us an example that for the task of image classification, the output stride for most of the models and classification is 32, but for the task of semantic segmentation, we would definitely need to preserve so many spatial information because we want to segment each pixel and map them to a label. So in this part, the spatial information becomes so much important, and we need to preserve it much more than the classification task. So we can apply the output stride of like 18 or 16 for dense feature extraction, and the paper suggests that the output stride of this model is set to 8, and in experiences they show that how do they influence the accuracy of the model or minimum intersection over union score. So in this part, you can say that after the DeepLab version 3, using the DeepLab version 3 as an encoder, we also use the Atrous spatial pyramid pooling module, which we referred to it earlier in the picture, and to apply Atrous convolution with different rates. So that's how we capture the multi-scale information from our feature map. And also, we also have to note that the encoder output feature map contains 256 channels and is rich with semantic information. So the decoder model, after we considered the encoder and the design of the depth-wise separable convolution and all of these operations, we have another component, which is the proposed decoder, and we use the output stride of 16 for this model. And what it's saying is that we first bilinearly upsample the output from the encoder by factor 4. And as you can see, we concatenated with the corresponding low-level features from the network backbone. I mean, the network backbone could be a ResNet or exception or whatever it is. And in this example, we will we will catch the COM2 layer of the ResNet 101 to as the low-level features to combine it with the upsampling process. After we extract the low-level features from the intermediate level layers of ResNet 101, we apply another 101 convolution on the low-level features so that we could reduce the number of channels. And because we want to reduce the number of channels owing to the fact that we have limited computational resources, and if we have so many number of channels, maybe our network would give so much attention to the low-level features. So we need to fix it to a constant number. So we will apply a 101 convolution on the low-level features. And after that, that we concatenate the low-level features with the the output of the encoder upsampled by 4, we will apply a few 3x3 convolutions, as can be seen here, to refine the features, followed by another simple bilinear upsample by factor 4, which gives us the mask that we need for our original picture, and that would give us the output feature map that is in the original image size. And they also suggest that using output stride of 16 for the encoder module strikes the best trade-off between speed and accuracy. So it's better to use the output stride of 16, but it always depends on the dataset that you're using. If you're using for like small objects, you might want to consider another output stride. So it just depends on the network or dataset you're using. But the best factor is 16 that has been conducted in experiments and resulted the best in the best performance. So there's another thing that has been proposed in this paper, which is the modified aligned exception. Exception itself is just a classification model. So you can use this as your backbone, and we need to make some modification to make it work better. And they have made some modifications to the architecture of this exception that I will shortly point it out. So there's three main modification made to the architecture of this. The first one is that the first component of the exception model is that the entry flow network, they have kept the entry flow network structure the same, and they do not modify it for computation and memory reasons. But the second part, in the second part, all of the max pooling operations have been replaced and substituted by the depth-wise separable convolutions with striding, as you can see here. And in the last part, they have also added extra batch normalization and the ReLU activation after doing the depth-wise 3x3 convolutions. If I want to show the architecture here, you can see that the entry flow has been preserved the same, but we have changed this red highlighted layers to be separable convolutions, and they have some with the stride of 2, and also we have some skip connections also, which is followed by a convolution. And you can see the whole architecture of the exception that is modified, and the modifications are all are all summarized like this. But this is another backbone option that you can choose to use as the feature extractor in your encoder. But you can have multiple options to choose that, like ResNet or MobileNet, and there are some multiple others. So you can choose based on your needs. So this is how it works. There are some training details that I'm not going to go through it, because if you want to get further details about how these are implemented or how the training parameters are set, you might want to go through the paper to find it out. But the major points are pointed out like all of this. And the decoder design choices has been analyzed here, but the latest part and the final result shows that the decoder module, we consider 3 places for different design choices. So they have the 1x1 convolution to reduce the channel of the low-level feature map from the encoder module, and as we said, it is used to reduce the number of channels. And we have a 3x3 convolution after the concatenation to obtain sharper segmentation results. And the low-level features that has been obtained from the intermediate level of our backbone model to help the decoder to better recover some spatial information. So it is also pointed out in here that why do we use a 3x3 convolution after the concatenation? The reason for using that is that after we concatenate the feature maps and channel reduced Conv2 feature maps, we have to do a 3x3 convolution with 256 channels, or as you can see in here, to refine the feature map, so it would become more clear for generating the mask for our input image. So that's how it's done. And there are some experiment results of using multiple different backbones. As you can see in here, the ResNet 101 using it as a network backbone gives us the results of this. As you can see in here, if you use the decoder, or if you use the flip or MS or any of these, would result in better or worse accuracy. You can check it out yourself. And for the same as the ResNet, you have the exception as a network backbone, and they have some results for using this as the backbone. And you can check it out for different options that you have for different configurations of the architecture and how it affects the MIOU score. So you can check it out yourself and choose the config that you based on your needs. So yeah, they have comprehensive information about these in here, and this is how all of its architecture has been formed. And generally, you could say that this new version of the DeepLab version 3 Plus, it has just made some minor modifications, but they have gained a substantial amount of performance on the benchmark data sets. And as the paper suggests, it mainly comes from the incorporating and combining two different architectures, which is used in most of the segmentation task architectures. And that is the Encoder-Decoder and the DeepLab version 3. And in this paper, you can see that they have used the DeepLab version 3 Plus as the encoder, and they have chosen a backbone model for the encoder. And for the decoder, they have upsampled the results in 2 steps using the low-level features and low-level feature maps to better recover this spatial information. So that's how the architecture has been designed so far. We've covered some of the salient points and motivations behind designing such a architecture and the reasons why this works better, and see the improvements of this on the famous benchmark. So that was a general overview of this architecture. I hope that you find this video useful and helpful to better understand how this is working. And thanks for watching and making the time for watching this.